Everyone, and welcome to part 2 of this lesson. In this video, we're going to look at all the algebra and all the things that are going to be happening as we approach limits. So we looked at a lot of graphs and properties in our last video, but now we're going to only be looking at functions. So let's get started. All right, so first we're going to be looking at the basic limit rules. So if we have a constant, if we have a value of x, or what we do when we have exponents. So let's go ahead and get started. So in the very first one, very straightforward, find the limit as x approaches 3 of 5. Well, think about the graph of 5. That's just a constant, right? And as I approach 3 from the left and from the right-hand side, it's still just going to be equal to 5. So any constant, pretty straightforward, is going to be equal to whatever that constant is, right? So now let's look over here, part 2. And you can look at the graph of these, but we're going to do this from an algebraic analytical approach. So the limit as x approaches 2 of 4x squared plus 3. And let me show you how to write this out step by step, because you don't want to drop any of these. And at the end of this video, we're going to be looking at some of the mistakes that a lot of calculus students will do that are going to cost some points. So the limit as x approaches 2 of 4x squared plus 3, okay? So that was just me rewriting the problem. Now I'm going to apply the algebraic steps, which is saying, okay, just plug 2 in for x. So that's going to say equals 4 times 2 squared plus 3. So see how I'm showing that I am now finding the limit. And now that I'm applying the limit rules, the limit disappears, all right? And now I can just calculate this. 2 squared is 4. 4 times 4 is 16 plus 3 equals 19. Okay. Now, how do we apply this when we have a quotient? So let's look here at example 3. All right. You don't want to just go willy-nilly. A lot of people will do this, and a lot of problems, it's a shorthand, it's acceptable, but I want to be very clear and specific in this video because this is where you're learning it for the very first time. We're going to find the limit as x approaches 1 of the numerator, x squared plus x plus 4, over the limit as x approaches 1 of the denominator, x plus 1. And now I am going to show that I'm plugging in our values, 1 squared plus 1 plus 4 over 1 plus 1. Now I can drop our limits, equals 6 over 2 equals 3. Okay, so very, very clear about when you're putting in your limits, how you're applying them. This is going to be very important as we apply and learn some new rules in future lessons. And then over here, example 4, same deal, just throwing in some trig. We can just kind of rewrite our limit. The limit as x approaches pi over 2 sine of x. You don't need to rewrite the problem. But again, I'm just kind of showing you when I am getting rid of the limit sign. All right. And so then that is just asking us what is sine of pi over 2, and sine of pi over 2 is equal to 1. Okay. All right, so that's some algebraic approaches, but we're going to have to actually dig deep into our box of tricks for what we're going to learn about in our next section. So let's go ahead and look at this. So in some cases, we are going to get some values that we can't find, okay? So let's look over there at example 6 real quick. The limit as x approaches 1 of x cubed minus 1 over x minus 1. I'm going to kind of do a bit of a shorthand here that I just told you not to do. But let's say, okay, I get 1 minus 1 over 1 minus 1, which equals 0 over 0. All right. 0 over 0 is not 0. It's also not equal to 1. That is what we call an indeterminate form. And when you get an indeterminate form, that means you have to do more work. And I'm going to formalize what that is going to look like in some future videos. But for now, what we're going to say as we do these problems is, okay, the limit as x approaches -3, you can't do a direct substitution. What I want us to show, I'm not going to explain in this video because it's going to be a little bit more important to kind of learn some of the processes here. But what we can do is kind of rewrite our problem. The limit as x approaches -3 of the numerator. And what I can do is factor the numerator. So in the numerator, get x plus 3, x minus 2. And in our denominator, we get x plus 3. So all I'm doing is rewriting the problem here, right? And what we can do is factor these out. So we can factor out these things. X plus 3 disappears. And then we can rewrite our problem, the limit as x approaches -3 of x minus 2. So notice how I haven't dropped my limit yet because I haven't substituted for x. Okay, now I'm going to substitute for x, -3 minus 2 now, and I get -5. And so we have now solved the limit. So let's kind of look at our next example here, example number 6. X cubed minus 1 over x minus 1. So in here, the numerator, we have actually a difference of cubes, x cubed and 1 cubed, okay? So again, as I showed earlier, we can't directly substitute 1 into this problem because we get that indeterminate form, 0 over 0. So what we're going to do is factor. So the limit as x approaches 1, and we're going to see and hope that something's going to factor out. And so in our numerator, we are going to get x minus 1 times x squared plus x plus 1, all divided by x minus 1. And yes, something does divide out the x minus 1s, okay? So I'm going to rewrite what we had, the limit as x approaches 1 of x squared plus x plus 1 equals, well, now I can substitute that 1 in. So 1 squared plus 1 plus 1, and I get 3. Okay, so when we can factor things out and then they're going to divide out and disappear, we rewrite the problem with the limit still there, and then we can just make our direct substitution. Now let's look at the next type of problem when it's not going to work. Again, always try direct substitution first. Can you plug in 0? And get out a value, then you should be rewriting your limits and calculating the value. All right, so 0 plus 1, I get the square root of 1 minus 1 over 0. And so I get 0 over 0, indeterminate form, which means I have to do more work. All right, so let's go ahead and examine what that more work looks like in this kind of conjugate problem. So in this case, what I'm going to do is I'm going to multiply by the conjugate, the square root of x plus 1 over the square root of x plus 1 plus 1. All right, so the conjugate means whatever this sign is, I kind of just swap it. And this entire quotient is just being divided by itself. So that's, I'm just essentially multiplying by 1. All right, so let's kind of look at what happens here. We're going to FOIL out the numerator. So the square root disappears. That's going to say x plus 1. The inside and the outside are going to cancel out because one's positive, one's negative, and then we're going to get minus 1. And then in our denominator, with these type of conjugate problems, it's always best not to multiply these things out. So I'm going to leave the x as it is, and I'm going to multiply it by square root of x plus 1 plus 1. All right, now in my numerator, oops, I have made a small mistake, but I need to still write the limit as x approaches 0. Have I found the limit? No. Have I substituted in the limit? No. So I still need to be rewriting that limit as I go. So the limit as x approaches 0, we're going to go ahead and in my numerator, these ones divide out. So I just have x divided by x. Those divide out as well. Okay, so we're going to have the limit as x approaches 0. When I divide out these x's, I'm going to get 1 in my numerator divided by the square root of x plus 1 plus 1. And now I'm holding on to the limit still. Now I'm ready to substitute in that 0. So I'm going to get 1 over the square root of 0 plus 1, which is 1 over 2. So 1/2 is the value of that original limit. You don't leave it at 0 over 0, that indeterminate form, because you can do more work. Now let's look at this next problem, which can get kind of complex, but when we have a lot of fractions. So again, the same reasoning in our last several examples, you are getting an indeterminate form of 0 over 0. So now we have to keep going, And what you want to do with these complex fractions is kind of see what work you can be doing. So let's combine the fractions in our numerator. So if I do that, how is that going to look? Well, I'm just going to come in here. I'm going to multiply this one by 3 over 3 and the second one by x plus 3 over x plus 3. Okay, so let's just see what happens. I'm going to rewrite my limit as x approaches 0. I'm going to get 3 over x plus 3 times 3 plus, sorry, not plus, minus x plus 3 over 3 times x plus 3. All still over x. So these fraction problems are going to get a lot more complex before they become simplified. But again, it's just about, all right, let's see what happens. Well, when I distribute this minus sign, I'm going to get a minus 3 right here, right? Okay, so that's going to be 3 minus 3. Those cancel out. And in my numerator, I'm going to be left with, limit as x approaches 0, of negative x over 3 times x plus 3 all over x. Well, remember this x in the denominator, this one right here, well, that's just x over 1, right? So what I can write is the limit as x approaches 0 of negative x over 3 times x plus 3 times 1 over x. And when I multiply by that 1 over x, these are going to divide out. All right. So now I am now determining the limit as x approaches 0 of negative 1. Don't forget that negative sign, because that negative sign over there is still there. So negative 1 over 3 times x plus 3. Now we can make our substitution of 0. So negative 1, I'm making my substitution. So that means I can drop the limit and I get 3 times 3, which is negative 1 over 9. Okay, so these are some examples that you can follow as you start to do a lot of these practice problems. These are all skills that you learned in your previous years, but they're going to come in and help you simplify a lot of these limit problems. Now let's look into example 9 here. What about when you have these x plus h's, okay? So again, always try and see what happens when you put in 0 for h. And what you're going to end up seeing is everything's going to divide out, everything's going to cancel out, and you're going to get 0 over 0, okay? So what can we do? Now, unfortunately, the only way to really approach these problems is to kind of go through the long algebra and expand everything out in your numerator, see what cancels out, and hopefully you can factor something else out at the end. So let's take some time and speed through this and see what happens in the numerator when we expand that all out. All right, so right here, I'm going to see, all right, what can I cancel out? So 4x squared minus 4x squared. I see a minus 3x and a plus 3x, and I see a plus 2 and a minus 2. All right, so let's rewrite our problem again. The limit as h approaches 0 of 8xh plus 4h squared minus 3h all over h. Now, what I notice in my numerator is that all three of those terms have an h in common. All right, so let's go ahead, factor out that h. So the limit as h approaches 0 of h times 8x plus 4h minus 3 all over h. And look at what happens. We can now divide out these h's. Okay, so we're going to divide out the h's. I'm going to move over here to make some more room. And I'm going to have the limit as h approaches 0 of 8x plus 4h minus 3. Now let's take away and calculate our limit, plugging in 0 for h. So we're going to get 8x plus 4 times 0 minus 3, which is equal to 8x minus 3 when we simplify it. So in this case, you're not getting a number, you're getting another function out, which is going to be very important as we move on to unit 2. But notice again, this is going to be the strategy that you can employ. You're going to have to expand everything out, cancel out everything that you can. And in many cases, and every problem that you're going to be solving in Calc AB is going to have an h that you can factor out. Then you're going to divide it out, and then you can substitute in your value. Okay. So now let's look into our last example with piecewise functions. Okay, so in this piecewise function, we're going to be approaching 2. But what you want to notice here is that when we approach 2, our function is changing. So with piecewise functions, you need to decide which function you're going to plug it into. But in this case, we're going to go back to the definition, is that we're going to have to find the left-hand limit and the right-hand limit and see if they're equal to determine the limit as x approaches 2 of f of x, because it's defined as a piecewise function. So we're going to break this down, the limit as x approaches 2 from the left of f of x, okay? And that is going to be our our second equation, x is less than 2, so from the left side. So then that is going to say the limit as x approaches 2 from the left of 5x plus 2, which is going to be 5 times 2 plus 2, which is 12. So now we're going to do the exact same thing, but from the right-hand side, the limit as x approaches 2 from the right of f of x, and f of x is going to be values greater than 2. So that is going to be the limit as x approaches 2 from the right of 3x squared minus 1. So that's going to be 3 times 2 squared minus 1. 2 squared is 4 times 3 is 12 minus 1, which is 11. So does the left-hand limit and the right-hand limit equal? No, they don't. Now, if we didn't have that minus 1, they would be equal and we would have calculated the limit. But in this case, the limit as x approaches 2 of f of x does not exist. Okay, and we had the proof that they don't exist because it says there 12 and 11, and 12 does not equal 11. All right, so I want to kind of finish up this video by looking kind of what I've been talking about with these common limit notation errors. All right, things that you want to keep in mind. So first, this correct notation. As x approaches 3, we have some sort of quotient. We can factor the numerator, but notice here, the entire time the limit is being carried through. We divide out these values. We still carry the limit because we haven't substituted anything in. Now, when we make our substitution, the limit is gone. We don't keep writing it, and we just make our calculation. So that's how we do it here. Now, these are the mistakes that students will very often make, okay? Notice this limit does not get carried through. So now you just have the function x minus 4. Where is this 3 coming from? You are going to lose points because you're not taking that limit all the way through. It's like losing a plus sign or losing a minus sign randomly. That is a function that you need to carry through until you calculate it. Now, what's next is when you have these empty limits. What we mean by empty limits is like you're saying the limit as x approaches 3 equals something. No, the limit is a function, okay? It is something that you're calculating. It is of something. So that limit needs to be with something. It is not something that you just equal to, all right? Oftentimes, students in this case are going to be dropping the values. They're just going to be writing limit, limit, limit everywhere. But you have to write where that limit is being calculated at. Don't forget that. And then lastly, this is a big one, is that when you make your substitution for x, you have to drop the limit. That is the time to drop the limit. You have to drop it, okay? If you don't drop that limit, then where did this 3 come from? Why are you doing this, okay? When you substitute, you have to drop the limit, okay? So don't have these extra limits that keep going through, all right? All right, everybody, thank you for joining this video. I know there's a lot of algebra here, but it's stuff that you've worked on before and you're just going to keep refining it here in AP Calculus. So we have one more video in this lesson. I'll see you all in the next one. I'm Mr. Hernandez. This was Mr. Hernandez Teaches.